Greetings from Dublin, Ireland, and good afternoon, everybody. This is my tape lecture, which I will upload after the taping for Tuesday, February 26th, which is today. Hopefully you will receive this before our 3:30 class today. Now, in this tape lecture, I will give a number of examples of microprogramming as a further illustration of the microprogramming concepts I introduced last week. Our first example will be a simple subtraction where we subtract register B from register A and put the result into register A. So this is something that we can actually do with one microinstruction in VESP. And as you can see, all we have to do is to select A on the A bus, select B on the B bus, and then set the ALU function to A plus not B plus 1, and then select A as the destination for the result. These translate into a single microinstruction on VESP 2.1M, and here's how. We simply put A on the A bus, as I just said, B on the B bus, and O bus equals to this, which is A minus B, and then O bus goes on to A. Now, this is a microinstruction, which is a transfer kind. Therefore, we put 0, 0, and 0, 0, 1 simply allows us to select A onto the A bus. 0, 1, 0 allows us to pick B onto the B bus, and then the O bus simply performs this operation, the ALU that is, to make this expression go on to the O bus, which is A minus B, and that is affected by 0, 1, 0, 0, and finally we put the O bus contents into register A. Now, so you can write this binary code and then convert that into hexadecimal rather easily by taking these in 4 bits at a time. So that was a simple example. In the next example, I will simply do the following operation, that is, A equals to A plus B. We can do this with 2 microinstructions. First we do A equals to A, and then do A equals A plus B. Now, 2A is easy to do, which is simply a shift of A by 1 bit to the left. So, and then after that, of course, addition is just as easy. So we have 2A plus B, and A is equal to A. B bus, we don't need to select anything onto it. O bus equals, this is not B bus, but A bus. So let me just quickly change that. And then have that change made, after which we have A equals O bus. So with these, now we have a microinstruction, which is again a transfer kind. So that's why this is 0, 0. So we pick 0, 0, 1, picks A onto the A bus, and B bus doesn't really matter. We could have written anything here. And the O bus is now the left shift of A bus. And then finally, we take things into A, which would have been, again, a minor mistake here on my part, would have been 0. So with that change, now we have this binary representation, which translates into 0, 0, 0, 4 zeros will be 0, and then 1 followed by 3 zeros will be 8, and then another 1 followed by 3 zeros would be 8, and the last would be 0. Now, having done that, we now have to simply add the 2 together, A to B, and that's what exactly this microinstruction does. So we have 0, 0, which is a transfer kind of a microinstruction. This is put A on the A bus and then B on the B bus. These are the 3 bits here for A and 3 bits for B. That's how we select those onto A and the B buses. And then we do O bus equals A bus plus B bus, which is equal to this, and then A equals O bus, which is basically how this code allows us to do that. And again, once we have this written up, we can then simply copy everything from here into hexadecimal, which will then give us this particular pattern. Okay, so that was fairly easy. And now the next microinstruction allows us to do something a little more powerful, that is microcomputation. If A equals 0, we want to subtract 1 from IX. If it's actually not, which is to say that it could be positive or negative, then we have IX equals IX plus 1. So we can do this with 5 microinstructions. In the first microinstruction, we'll simply check to see if A is equal to 0, in which case we will just jump to the 4th microinstruction. That will have to be in location 3 if in fact we're jumping from location 0. We're starting out with that. And then the second microinstruction, we're going to increment IX because we haven't really jumped to decrement it. And then the third microinstruction will simply allow us to get out of that loop and simply exit out of this condition and to the end of the statement. And in the fourth and the fifth micro instructions, we're going to decrement IX by 1. Now, this will take 2 steps as opposed to 1 because of the location of IX on being on the B side as opposed to A side. You will see this momentarily as to why we actually need to put this in this fashion. And finally, the last micro instruction will simply the point of exit, which we will not get done anything there because that's simply a place where we exit out of this condition. Okay. So this is a rather longer looking micro code, but it's all the way the same way simple. And simply branch if A is equal to 0, and we do this simply by putting a 0, 1 on the left because that's a branch kind micro instruction. And then we pick the condition code select, which is basically 0, 0, 0, 1, which is to say we're going to branch with A being equal 0, and then we pick ourselves a location to branch, which is location 3. That's where we're going to do IX equals IX minus 1. If we don't branch, we're going to come down here and do the incrementation. But before that, so what you do, you write this binary code, again, convert that into this decimal representation. From what I can see, it's going to be 0, 1, 0, 0, which is 4, again 0, 1, 0, 0, which is another 4, followed by 3, and followed by 0, and then that followed by 3. Incrementation is something simple. You put 1 on the A bus and IX on the B bus, and simply add the 2 and put the result back into IX. That's going to give you this part of the conditional statement. And once you get that written up, and again, it's a transfer kind of micro instruction. We put 1 on the A bus and then IX on the B bus and so on. So these are basically binary patterns that are available to us straight out of the microsequencer code that I've written. And then with that, you have this binary, hexadecimal representation, which is basically 0, 0, 1, 0, which is 2. And then you have 0, 1, 0, 0, which is 4, and then you got 2, and then you got 3, which what this is. So after that, we do make a jump to location 5. Now, this is not the kind of jump instruction we did in VESP. If you recall, there was only a transfer instruction there because all we did was to place PC into, the address field of the IR register into the PC. Here, we're not doing that. We're actually physically jumping to another location in the micro store, okay? And we do this simply by writing another transfer instruction, branch instruction, micro instruction that is, and in this branch micro instruction, we put a condition here which simply says always jump. And always jump to where? To location 5, which is where we exit this program. So that is precisely what this hexadecimal code represents and allows us to make this jump. Okay, but it is a conditional branch where the condition is always true, so it's really like a forced jump. It's not like the jump instruction we executed in the machine level, in which case all we did was to take the address portion of the IR and put it into the PC. Once we do this, we have to do now the subtraction. This is where we would have done that. If in fact A were to be found to be 0, we would have come down to location 0, which is in the microstore location 3. And that we will do by loading nothing onto A bus, putting IX onto the B bus, and then selecting O bus equals B bus, and then writing that IX into the A side. Now, the reason we do it this way is we want to do the subtraction of 1 from IX. Now, the way that the subtraction works, that A must be on the left-hand side, and then whatever we subtract must be on the right-hand side. So IX goes to the left, and then 1 stays on the right, and that's how we subtract. In other words, the subtraction operation is oriented this way. A bus plus not B bus plus 1, which is A minus B bus, so that's why we had to carry IX into the A bus side and then add 1 to it by injecting it onto the B bus. So A by this time has IX and B bus has 1, and so we simply do A bus plus minus B bus plus, not B bus plus 1, that would really be nothing but A minus B, which will be IX minus 1. There's a little double B there. Let me just quickly take care of that, which I just have done. And we go back. And you can see that IX being in the A bus and B bus being 1, and then we do the subtraction, we obviously get IX minus 1, and that goes into IX, and that's the end of this particular program. So the last example is slightly more complicated, in which case we take something from a location in the memory of VESP, which is in this case location 8, and increment it by 1, and then put it into the same location. Now, in order to be able to access a location in memory in VESP, we really have to put something, the address, into MAR. Now, in this case, we need to load 8 into MAR. Now, we know that we only have 0 and 1 on the A and the B buses, so we cannot really create this 8 out of nothing. So one way would be to take that 1 on the A bus or the B bus side and simply increment, put it into one of the registers, okay? And in this case, we could put it into the MAR register, if you like, and then increment it 7 times. Now, I assume that MAR is on the A bus. If not, we can copy it into one of the registers like A or whatever bus we have on the left-hand side, and then increment it 7 times, and then copy that into MAR. But we can, so effectively we can do it, but all that means is that we're going to have to now do 8 instructions in all to be able to load 8 into MAR, which is not a desirable thing to do. I mean, if this were to be not 8 but 100 or 1,000, we would have introduced into our micro store a micro program which would have had about 1,000 instructions just to load a number into a register, which is ridiculous to do, clearly. So we need to find a better way to do that, and the better way to do that is to introduce another class of micro instructions, which we really have introduced already in our class last week in the second installment, and where we do have what we call micro store transfer micro instructions. We're actually transferring things from essentially the micro store, and these things will be constants that we need, like in this case, this constant 8. We could do this in both directions, even though in this case we just need to read this 8 out of the micro store. So one way to do that is to tap the micro store transfer type instructions, and those were identified by 2 1s on the left, and we had a read-write bit here, which we have to set to 0 for read and a 1 for write, and then we have the read-write address, which has to go in here. So in order to be able to give myself the option of having a constant like 8, but a whole bunch of other constants, I could, for example, reserve the last 12 locations in the microstore to set them to constants that would be basically these constants here, 0, 1, 2, 4, 8, 16, 32, all the way up to 1024. And then if I want to generate any number that will be a linear combination of these, I can then write anything that would actually simply take these or not take them, and that will be just a binary representation, if you like, okay? So effectively, I can do additions on these numbers that I stored in these 12 locations, and by adding them together, I can generate anything between 0 and 2048, okay? And some numbers will be readily available, and 8 is one of them, so I don't need any addition for this. But if I needed 9, I would simply have 8 plus 1 for that. So that would be something that I had to do. But for 8, I just have to go to the location that I've written down here, and that is where 8 is going to be located, and I'll copy it from there. So here's the instruction then that would let me copy 8 and store it in, I guess in this case, possibly in MAR, but if not MAR, maybe one of the other registers, and then I can copy it from there into MAR. So I think the way I set it up, I chose register B as the destination for this kind of operation, so that's why I load 8 into B from the micro store, and then copy B into MAR, and then read memory into MDR, and then copy MDR into A, increment it by 1, and then store it back into MDR, and then write. So that's, this has gotten to be a long microcode by the very fact that we now already have 7 steps in here. But you can see that, this is still feasible. All we had to do was to simply facilitate this loading of a constant into MAR indirectly through via B. I could have also elected to put it into MAR, but MAR is an address register, so I didn't want to mess with it too much, and instead I wanted to put it into B so I can copy it from there into MAR. Okay, so the first step is easy to implement. I put a 0 in here because it's a read, and then this is one for obvious reasons, because this is a micro-store transfer kind of instruction, and these ones, and then 011 is where exactly 8 is stored in the micro-store. That's how I elected to store those numbers, and then that's basically DFFB as a hexadecimal number. So once you put that into the B bus, copying it into the MAR, and then simply doing a read, and then taking MDR and putting into A, and then after incrementing A by 1, all of those are simple steps. And I think Manish will be doing a great job in his recitation classes to explain these things to you further, and you should have no problem with that. But just in case you want to go and really educate yourself further about microprogramming and other styles of microprogramming, etc., just know that we want to scratch the surface of machine and microprogramming techniques. And for machine programming, I guess Wikipedia will give you a good place to start. Microprogramming likewise, and so you have to click on these two links to be able to go there, but you know that you will do any link, any web browsing at your own risk. So hopefully this has been a useful a few examples of microprogramming, and if things have not been resolved, we could always try to address them when I get back this Thursday. So I look forward to seeing everybody this Thursday at 3:30. Until then, goodbye and take care.